Welcome back to Mechanical Engineering Made Simple. Quick update before we dive in. We've officially launched paid subscriptions. That means if you want deeper cuts, special episodes, and real answers to the questions engineers actually care about, you can now support the show directly. Today, we are getting into something really fundamental. We're going to be exploring how we actually measure the invisible fluid flow.
Right. And this is a huge topic.
It is. We're going to cover everything from, industrial pipes that are governed by standards like British Standard 1042, all the way to the really complex math you need to describe fluids when they start misbehaving.
Like hitting the sound barrier.
Exactly. We're looking at mechanical versus optical measurement, and then we'll dive into ideal flow models against, well, what happens in the real world with compressible effects.
And that's really the dual reality of fluid engineering, isn't it? On one hand, you have to be able to put a real physical number on a flow rate. For safety, for efficiency, for commerce.
That's the industrial standard.
That's the industrial imperative. But then, to truly innovate, if you're designing a pump or an aircraft wing, you need the theoretical side of things. We start with this beautiful but kind of flawed concept of an ideal fluid, and then we just keep adding layers of complexity until we get to supersonic shockwaves.
So the goal is to connect those two worlds for everyone listening.
Precisely.
Okay, so let's start at the very beginning. Pinpointing velocity. I think the classic starting point has to be the Pitot tube, or the Pitot-static tube.
It absolutely is. And what's so fascinating about the Pitot tube is how it uses this direct, almost foolproof relationship between flow and pressure.
So how does it work mechanically?
Well, the velocity is calculated directly from the difference between the total pressure, which we can call P1, and the static pressure, P2.
Okay.
And if the fluid is incompressible, you can often simplify the whole thing by using a Pitot tube coefficient C, that's just equal to 1.
Right. But real-world pipes are huge, and the velocity is never perfectly uniform across the whole thing. So how do you use a single-point measurement to get a mean flow rate?
That's a great question, because a single reading is, well, it's basically useless. The real nugget here is that you conceptually divide the pipe's cross-section
Into smaller pieces.
into concentric rings, all of equal area. Then you measure the velocity right at the center of each of those rings and average them out. It's a really pragmatic way to get a highly accurate mean flow velocity for the whole pipe.
But the standard Pitot tube is really only for simple one-dimensional flow. What happens when things get messy, like flow swirling around a turbine blade?
Then you need specialized tools that can sense direction as well as speed. For two-dimensional flow, you'd upgrade to something like a cylinder-type Pitot tube. People often call a yaometer.
And how does that work?
You rotate the cylinder until two pressure ports on it show zero difference. Once they do, you've found the flow direction. Then you use a third port to get the total pressure and, from that, the velocity.
And for 3D?
For truly complex three-dimensional flow, you'd move up to a 5-hole spherical Pitot tube.
Okay, so that's the classic mechanical stuff. But sometimes you need more speed, more precision. This is where things get really interesting when we turn to electrical and optical solutions. Let's start with the hot wire anemometer.
Yes. The principle here is just elegant physics. It uses a very, very fine wire that's heated electrically.
And the fluid cools it down.
The fluid flows past, whisks the heat away, and that changes the wire's electrical resistance. And that change in resistance tells you the velocity. It's that simple.
We hear a lot about the constant temperature anemometer, the CTA. Why did that model win out over the constant voltage type?
The key engineering insight is all about thermal inertia. You see, when you're studying turbulence, you want the system to respond instantly to tiny, rapid fluctuations in the flow.
To chaos.
To the chaos, exactly. The CTA constantly adjusts the current to keep the wire's temperature fixed. By doing that, you drastically minimize the thermal inertia. It gives you a phenomenal frequency response, up to 100 kilohertz.
100 kilohertz. That's incredible.
And that's the speed you need to capture the smallest, most crucial eddies in a turbulent jet stream. It's non-negotiable for optimizing something like combustion efficiency.
So if we push even further into high-tech, we get to the laser Doppler anemometer, the LDA. How are we using light to measure flow here?
We're using the Doppler effect. First, you have to seed the fluid with these microscopic tracer particles.
Okay.
When a laser beam hits one of those moving particles, the light scatters. But because the particle is moving, the frequency of that scattered light is slightly shifted. That's the Doppler shift.
And the LDA just measures that shift.
It detects that frequency difference, which we call f sub d. And that difference is directly proportional to the particle's velocity. You're basically using the speed of light to measure the speed of a particle down to the micrometer.
And there are a few different ways to set them up, right?
Exactly. The main ones are the reference beam type, the interference fringe type, and the single beam type. They're complex to set up, sure, but once they're running, they give you the best spatial and temporal resolution you can possibly get.
So that covers pinpoint velocity. Let's zoom out to the bigger picture. Measuring the total flow rate, Q. We're moving from point measurements to total system throughput. And the industrial workhorses here are the restriction methods.
Right. To get the total flow rate, you have to look at the entire pipe cross-section. This brings us to things like the orifice plate, the nozzle, and the venturi tube.
And they all work on the same basic idea.
They do. All three create a controlled constriction, which forces the fluid to accelerate. By measuring the pressure difference across that constriction delta P, you can calculate the flow rate, Q.
So if they're all based on Bernoulli's principle, why choose one over another? I know the venturi tube is the most efficient, theoretically.
It is, but the trade-off is often economic. A venturi tube has minimal flow loss, but it's big and expensive. Nozzles are a good middle groundless loss and bigger flow coefficients than a simple orifice plate.
But the orifice plate is everywhere.
It is, because even though it's inefficient and causes a big permanent pressure drop, it often wins out.
Wow.
Why it's cheap to make, easy to install, and you can just swap out the plate if you need to measure a different flow range. It's a classic engineering trade-off.
That's a great point. Now let's flip the script. Let's talk about area flow meters, like the rotameter. This one works by keeping a constant pressure difference.
Yes, the constant pressure principle. A rotameter has a float inside a vertical tapered tube. As the flow increases, the float rises, which increases the flow area around it.
And it finds an equilibrium.
It settles where the pressure and drag forces perfectly balance the float's weight. So the height of the float is a direct, linear, visual measure of the flow rate. Simple, cheap, perfect for low-pressure stuff.
Beyond pressure and area, there are a bunch of other devices. For integrated volume, we have positive displacement meters.
These are basically mechanical odometers for fluid. Things like oval gear or Roots-type meters physically trap and count a constant volume of fluid over and over. They're fantastic for precise batching.
Then there's the turbine flow meter.
Right. That one uses the fluid's kinetic energy. The flow spins a small turbine, and the volume flow rate is just proportional to the pulse frequency you get from the spinning blades.
What about the magnetic flow meter? You see this in high purity or really corrosive applications. Why is it so dominant there?
Its dominance comes from its principle, Faraday's law of electromagnetic induction. If you have a conducting fluid moving through a magnetic field, it induces a voltage and electromotive force, E, across the fluid.
And that voltage tells you the velocity.
And it's directly proportional to the mean flow velocity, V. The magic, though, is what it doesn't depend on. It has zero moving parts, causes zero pressure loss, and the reading is totally independent of the fluid's viscosity, pressure, or specific gravity. You just can't beat that for some industries.
Let's end this part with the vortex shedding flow meter. This one always reminds me of the Kármán vortex street behind a bridge pillar in a river.
And that's exactly what it is. You put a bluff body in the flow, and Kármán vortices shed alternately behind it. The frequency, F, of that shedding is directly proportional to the flow velocity, U.
And that relationship is stable.
Very stable. It's described by the Strohal number, which is about 0.2 for a huge range of industrial flows. You just measure that shedding frequency, and you've got your velocity.
Okay, that covers the brass tacks of measurement. Let's leave the factory floor and head into the theoretical workshop. We have to start with ideal flow, or potential flow. Now, everyone learns about velocity, potential, phi, and the stream function, CS. But be honest, is this stuff still relevant when so much work is done with viscous flow and CFD?
That's a great challenge. And the answer is yes, for two big reasons. First, for many large-scale flows where the Reynolds number is huge, the bulk of the fluid behaves as if it's non-viscous. It's governed by Euler's equations.
Oh.
Second, and maybe more importantly, potential flow gives you an incredibly powerful mathematical baseline for understanding things like lift and drag.
So tell us about those tools. What's the real utility of the stream function size?
The stream function psi is fantastic because it directly shows you the fluid's motion. Lines where psi is constant are the streamlines, the actual paths the fluid particles follow.
And the real magic?
The real magic is that the volume flow rate, Q, between any two streamlines, say psi1 and psi2, is just the difference. Q equals psi2 minus psi01. Calculating a complex flow volume becomes simple subtraction.
And what about the velocity potential, phi?
The velocity potential, phi, gives you the velocity vector from its gradient. A line where phi is constant is an equipotential line. And the beautiful part is that these equipotential lines are always at perfect right angles to the streamlines.
And they're connected mathematically.
Deeply connected. Both of them satisfy Laplace's equation, which is nabla squared phi equals 0, and they're linked through the Cauchy-Riemann equations.
Which brings us to complex potential theory. W of z equals phi plus ITSI. The idea here is that you can build complex flows by adding simple ones together.
That's the power of
Right.
superposition. We can define basic flows, like a source where fluid flows out, or a sink where it's absorbed. But the really clever component is the doublet.
And what is a doublet?
Mathematically, you create a doublet by taking a source and a sink of equal strength, moving them infinitesimally close together and increasing their strength to infinity as they approach.
It sounds incredibly abstract. What's the payoff?
The payoff is huge. If you simply superimpose a uniform parallel flow onto a doublet, you have just mathematically modeled the flow around a perfect cylinder,
Just by adding two simple functions.
just by adding them. It's an algebraic shortcut to calculating pressure distribution and theoretical lift and drag, avoiding a ton of complex calculus.
Okay, let's move to the extreme end now. Compressibility. When do we have to throw out the assumption that density is constant?
You have to account for density changes when you're dealing with gases moving very quickly or undergoing large pressure changes. The whole game changes, and it's all quantified by the Mach number.
Which is based on the speed of sound, a.
Exactly. Sonic velocity A is the speed a pressure wave moves through the gas, and the math shows it's proportional to the square root of the absolute temperature, T, hotter gas, faster sound. The Mach number, m, is just the ratio of your flow velocity, u to that sonic velocity, A.
And there's a rule of thumb for when it starts to matter,
Here
right?
it is. If m is below about 0.3, the compressive effects are pretty negligible. You can usually get away with treating it as incompressible.
So what physically happens when you push past that and hit Mach 1?
The way the flow communicates with itself fundamentally changes. In subsonic flow, when m is less than 1, pressure waves travel both upstream and downstream. But in supersonic flow, where m is greater than 1, the fluid is outrunning its own pressure waves. They can't travel upstream to warn the fluid ahead. These trapped waves form a Mach cone, where the sine of the cone's angle, alpha, equals 1 over m. The sound is literally trapped inside that cone.
Which is why you don't hear a supersonic jet until after it's passed.
That's the sonic boom.
This is critical for nozzle design. If I'm pushing air through a simple convergent nozzle, can I get it to go supersonic?
No. You can only get it to Mach 1, and only right at the throat. As you drop the downstream pressure, the mass flow rate increases, but only up to a point. For air, that point is when the pressure ratio hits 0.528.
And then what happens?
At that exact point, the velocity hits the critical velocity u star, which is equal to the local speed of sound, a. The flow is now choked. You can pull a complete vacuum downstream, and you will not get a single extra gram of air through it.
And that's what leads to the classic shape for supersonic engines.
Precisely. To get flow to accelerate past Mach 1, you have to add a divergence section after the convergent throat. That's the de Laval nozzle.
Let's make one last jump. From steady-state flow to the sudden, chaotic world of unsteady flow. We're talking about control systems, rapid changes.
Absolutely. A simple example is just the vibration of a liquid column in a U-tube. It's a simple harmonic motion, z equals z naught cosine of omega nt. Add friction, and it becomes damped. But the most critical unsteady safety issue is, without a doubt, water hammer.
And we're not just talking about a calculation. This is about ruptured pipes, millions in damage. This is a huge safety issue caused by closing a valve too quickly.
It's incredibly violent. When you slam a valve shut, all that fluid momentum is converted almost instantly into immense pressure energy. You get a huge pressure spike, delta P.
And you can calculate that spike.
You can. Delta P equals rho VA, where A is the speed of the pressure wave. And crucially, that wave speed A isn't just the speed of sound in the fluid. It's modified by the elasticity of the pipe itself, the diameter, wall thickness, the Young's modulus of the pipe material.
And the timing of the closure is everything.
It's the difference between a controlled stop and hitting a brick wall. If you close the valve faster than the wave's round trip time, that's 2L over LA, you get the maximum catastrophic pressure rise. If you close it slower, the pressure rise is far more gradual, governed by a Levy's equation.
What an incredible journey. We went from practical tools like the magnetic flow meter, which causes zero pressure loss, the amazing precision of a hot wire anemometer capturing turbulence at 100 kilohertz, all the way to the pure theory of complex potential that lets us model an airfoil. And then we finished with the dramatic physics of the Mach cone and choked flow.
The synthesis is what makes this field so fascinating. And here's the final thought to mull over. The same purely theoretical math, I'm talking about conformal mapping techniques, that we use to model flow around a perfect invisible cylinder to predict its aerodynamic behavior. That is the exact same mathematical tool we use to calculate the real, messy, physical contraction coefficient of flow coming out of an orifice in a giant industrial tank. The theory is never truly separate from reality.
Fascinating stuff. That's all the time we have for this deep dive, but if you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple by Strike Vision Studio, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use.